So in the next lecture, we'll look at forces and moments. So let's just introduce the topic. So basically, I have a rigid body, which is, again, there is an origin OA and some x-axis, y-axis and z-axis. There is a force which is acting at a point P, which is located by a vector AR. Okay, so AR means it's a point with respect to this A coordinate system. And this force F1 is shown by this arrow. It is acting at this point in the rigid body. The moment of this force about OA is nothing but R cross F. Okay, so I take this vector and I take this force vector, and then you do a cross product, which is AR cross AF. Okay, remember, everywhere in all mechanics or in all algebra like this, if you do any vector operations, the two vectors should be in the same coordinate system. So in this case, AR means it is a radius position vector in the A coordinate system, and this force is also described in the A coordinate system. Suppose I want to find out what is the moment of this force about some other point OB. Okay, so where is OB? OB is located from OA by another vector AR AB. So it's a vector from A to B, and which is given by RAB, and again it's in the A coordinate system. So the moment of AF1 about OB is MOB. We write a symbol like this, and this is AQ, which is this point here. OB to this is this vector AQ cross AF1. Okay, so the moment about OA is ARA plus this. Okay, so what you can see is moment of about OA, which is this quantity, is nothing but this vector plus this vector, and then we have to do this proper cross product, and the cross product of this part is MOB. So we will see how it is useful little later. So now we have this rigid body. Let's take another scenario that there are lots of forces, F1, F2, F3, all the way till some Fk, which are acting on this rigid body, and these are acting at different points. So F1 is acting at AR1, F2 will be AR2, Fk is acting at ARK, and so on. So we can simplify, instead of considering all these forces, okay, we can think of it as an equivalent system. These three lines means it is equivalent to a single force which is acting at some point and a moment. And this line of action of this F is the resultant of all these forces. So how do I find out F? It is nothing but vector sum of all these individual forces, F1, F2, all the way till Fn. And what is the moment, equivalent moment? It is ARI, again sum over all these n forces, cross Fi. Okay. So if you have, in addition to all these n forces, F1 through Fn, suppose this rigid body is also subjected to n at moments. Okay, so I have M1, M2, all the way till Mn. So now we can say that the resultant moment about OA for all these forces and moments are nothing but the sum of all the moments, I equals 1 through n mi, and sum of all the moments of these forces. So it is Ri cross Fi. Okay, so the resultant force is nothing but sum of all the forces, which is as before, but the resultant moment about this origin point OA is the sum of all the moments plus the sum of the moments of each of these individual forces. Let's now go forward and look at what are some of the common forces which you are seen in mechanical systems. The first most common force which you will see is something called as a contact force. So if you have a rigid body I in contact with another rigid body J, okay, so at the point of contact there will be two forces which are acting. So this Fij is the force on J due to I, and this is equal and opposite to the force on I due to J. So Fij is same as minus Fji. Okay, these are equal and opposite because of Newton's third law. Okay, so those, most of you know what is Newton's third law, that if you have some body which is resting on the ground, there is an equal and opposite reaction forces. So Fij will be same as minus Fji. Another very common element which is seen in mechanical system is a spring. Okay, so in the case of a spring, suppose there is a mass which is here, okay, and then it is attached to some kind of a wall or a fixed reference using a spring. The spring is defined by a spring constant. Okay, and what is the spring constant? It's a number which is related as some F equals kx. So if this object is displaced by delta x, there's a force due to the spring which is acting opposite to the direction of this displacement, and that is given by F equals kx, k delta x. Likewise, we can have what is called as the torsional spring. In that case of a torsional spring, there's a torque which is developed when you rotate a body, okay, by theta. Again, k is the spring constant. So remember, in one case it is a linear spring, in this case it is a torsional spring. So the units of k are different for both of them. You can also have a damping force. Okay, so a typical damping force can be shown in this form. So I have an object and then it is moving towards the right by some x dot. This is the damper, okay, a schematic of a damper. This is a schematic of a spring. So what you can see is that when it is trying to move towards the right, a force which is developed which is bringing it back. So this is, if the force is c times x dot, so basically if the force is proportional to x dot, this is called as a viscous damping. You can also have a damping force which is some constant plus c2 times x dot. This is called as a Coulomb damping, C1 part, and this is called as the viscous damping part. So in general, you can have a damper or a force which is resisting this motion. Some part is constant and some part is proportional to the velocity of the body. Friction force is another one which is very useful and interesting. And this occurs when you have an object, say a mass m, which is on some surface, and then there is a weight or a normal force which is acting on the mass. So N is the normal force. Most of the time it could be like simply weight. So N could be m into g. G is the gravity. So if you have this velocity in this direction, a force develops in the opposite direction. Okay, the magnitude of this force is mu times n, where mu is a constant. And this is again must have seen earlier. So there is some relationship between the friction force and the normal force, and this is called the coefficient of friction. Okay, some typical values, how much would be mu? So maybe 0.3. If it is very smooth and if it is very slippery, there is some oil between this mass and the ground, then this mu will be smaller. And how does this friction force change with x dot? Typical values is it starts from some constant value. As soon as it starts moving, it decreases this friction force. And then again it will start increase, because then this part is dominated by velocity. Initially it is dominated by the static friction, and this is the dynamic friction. There are many such models. I have just shown you one very simple model, and there are lots of papers and lots of research which are still continuing to find out what is a good model of friction. Okay, so this is one reasonably good model, that we have some static friction, and then as soon as it starts moving, this value f decreases, and then as the speed increases, again it increases. Now this is not necessarily linear, it could be some curve also. You also have this very common force, which is the gravity force, and most of you would have seen what is gravity, but nevertheless, let's go over it once more. So if you have two particles of mass m1 and m2, and it is separated by a distance r12, okay, it's a vector from m1 to m2, r12. And what is r12? It is this location of this m2 minus the location of ar1, the location of m1. So if you have these two particles in 3D space, so there is a force which is acting between these two particles, which is given by g m1 m2 into this distance squared. Okay, and this g is the universal gravitational constant, and there's a minus sign which tells you that this is an attractive force, meaning that this, if you just leave it, this distance will decrease. So gravity is an attractive force. It is an equal and opposite force. So this mass is being pulled towards this mass, and m1 is pulled towards m2, and this attractive force is given by g m1 m2 divided by this distance squared. It is inversely proportional to the distance between the two particles. Okay, that is very useful and important. And it is always along the line connecting these two particles. G is a gravitational constant. It is a very important and a well-known number. It is given and available in many textbooks. So G is 6.67430 into 10 minus 11 Newton meter square per kg square. So is this a large number or a small number? Okay, so think about it. Is the gravity very important, very large force, or a small force? So if you have two masses, let's say each 1 kg separated by 1 meter square, okay, then what will you get? You will get this many newtons. So it's not very large, right? But in astronomy and in space, we have these really, really large masses of galaxies and suns and planets and stars. So G is important. Then it is not very important if we have two particles of 1 kg mass, 1 meter separated in your lab. The force on a mass m near the Earth's surface is m into g. Okay, so what is g? G is some number which is, so m1 is, let's say, one of the masses, my g m2 into r2 square, where r now is the radius of the Earth. Okay, and if you have a particle sitting on the surface of the Earth, you will get, of mass m, the force will be m into g, where g you can calculate, it is 9.81 meters per second square. Let's look a little bit more interesting extension of this gravity. So what we have here is a mass, a long rod of some form, okay, and there is another mass which is at some origin of a coordinate system. The center of mass of this long rod is at a distance r. Okay, the length of this rod is L, so it is L by 2 on both sides. So what we have here is a vector which is from the origin of this capital M through the center of mass, and let's call this vector A1. Perpendicular to this vector you have A2. We can also assign a coordinate system B1, B2, and of course B1 cross B2, which is coming out of the page, at the center of mass. So B1 is along one of the principal axis, B2 is perpendicular to that, and so on. And let's pick a point D, which is here. Okay, this is at the vector D, and a small element dx here. So what do I want to find out? That we have an extended rigid object of mass m, length L, with a center of mass at C. The object's center of mass is at distance r from a particle of mass m. So you can think of this as Earth, and this is a very long satellite. Okay, so this mass m is at the center of Earth, and this extended object is a long satellite. So what I'm going to show you next is that this mass m can interact with this long object through gravity, but it is not only a force. It can also cause a moment on this body. So basically, it is not a force which is acting along this line. It is one force will of course be there, but this extended object can also rotate, meaning that there will be a torque which will act on this extended body. So I'm going to derive an expression for the mass m and this extended body, and how it results in both an attractive force as well as a torque. So here is some quick derivation. So as I said, we see this small element which is at a distance d. So what is the force, elemental force, which is minus g m prime. M prime is mass per unit length by d square, because it's at a distance d, and then there is a small element dx. Okay, so the force along A1 is minus g m prime dx d square into cos theta. Okay, the force along A2, which is the perpendicular direction, is this into sine theta. So this is the angle theta. And the total force is the integral of df1 and df2 over the length L. So from this triangle ABD, what you can see is this d square is nothing but r, which is, remember, this is the center of Earth, and C is the center of this extended object. So this is r square. But then you have this small angle x cos psi whole square plus x sine psi whole square. So this distance from here to here, d square, is nothing but this plus this, and this is r plus this small distance plus this distance. So where cos theta is r plus x cos psi divided by d, and sine theta is x sine psi divided by d. Okay, so what am I trying to do? Basically, I am trying to find out what is the net gravitational force acting on this long extended object, and if there is any moment also. So what is the integral of F1? So we want to integrate from minus L by 2 to plus L by 2 this quantity, which is minus g m prime into r plus x cos psi, and this is r plus x cos psi square plus x plus sine psi whole square to the power 3 by 2. Okay, why is this 3 by 2? Because it is distance of r square. Okay, but then there is already a square here, and this is like a unit vector. So if you think about it, you will get this formula. Okay, so we can take out minus g m prime outside and capital R square outside, and then we can rewrite it as 1 plus x by r cos psi, and then denominator is 1 plus x square by r square 2x by r cos psi to the power 3 by 2 dx. Okay, so what do we have now? We have this numerator is like 1 plus ax, and the denominator is like 1 plus bx square plus 2ax. Okay, so x by r cos psi is a, b is 1 by r square, so you will get this. Okay, so then what we have is we want to use binomial theorem. So we want to expand this as a binomial theorem. Why? Because some 1 plus a to the power ax to the power minus something, we can expand it in binomial theorem. It will look like this. So it will have 1 plus ax, then you have some 1 minus 3 by 2 bx square minus 3ax plus some 15 by 8 b square x4 plus 15 by 2 a square x square plus all these terms. Okay, so we are only going to keep these many terms. All the higher order terms we can remove. And again, why? Because we can see a is small, divided by r. So we will apply to the radius of the earth, which is very big. Even b is small, 1 by r square. So we don't need to keep all this b to the power 4 and all these higher order terms. So essentially what we get is this integral f1 is minus g m prime by r square, integral from minus L by 2 to plus L by 2, because that is the length of L is the length of the extended object, and then we multiply these two and again keep only some of the up to terms which are square. Okay, so it is 1 minus 3 by 2 bx square. Then you will have some terms which are coming from ax. So it is minus 3ax and so on. Okay, so basically what we have done is we have simplified this quantity which we want to integrate. We have used binomial theorem and we have kept only some lower order terms. Then we can integrate, and then you can show when you integrate that you will get g minus g m prime r square, and inside when you put the limits you will get 1 plus L square by 8r square into 2 minus 3 sine square psi. Likewise, we can find the perpendicular component, which was, remember, into sine theta. So we have minus L by 2 to plus L by 2 g m prime d square dx into sine theta. Again, we make all these expressions. So sine theta and so on, which is 1 plus x squared by r square, 2x by r cos psi, again to the power 3 by 2. And then again we keep terms which are up to some order. So it is like cx into 1 plus bx squared plus 2 abx minus to the power minus 3 by 2. A is same as cos psi by r, b is same as 1 by r square, and c is sine psi by r. Okay, so then again we keep terms which are up to some order, square basically, and we are left with cx minus 3a cx square dx. Okay, so the f2 component, which is perpendicular to the line of action from center of the earth to the center of the extended object, and this is perpendicular to that, this is along a2 direction, is given by this. We need to now evaluate this integral, and if you integrate you will get f2 as g m prime m L by r square, then you have some L square by 4, then you have cos psi by r, then you have sine psi by r, and we can simplify this writing cos psi into sine psi, 2 of that is sine 2 psi, and then we can write L square by 8r square and so on. So what is the net force? It is F1 plus F2. F2 is along direction A1, F2 is perpendicular to that. So we have minus GMM by R square, and if you rearrange it a little bit, you will see that you will get one term which is along A1, and this minus, because there is another minus here, so this will be L square by 8R square sine 2 psi into A2. Okay, exactly same thing is coming here. So the force which is acting on this object, it is along the radial direction and also perpendicular to the radial direction. We can also now find the torque which is acting perpendicular to A1 and A2. Okay, it will be along a direction A1 cross A2. So what is the torque? It is F2 cross R along A1, A2, and this again we can simplify and show that this is minus GMM L square by 8R cube into sine 2 psi into A1 cross A2. Okay, and does it make sense? Little bit, yes, because if this length of this extended object divided by r, which is basically the radius of the earth or some large distance, is small, then we get f is gm minus gmm r squared by a1. Okay, so if you have a particle, not an extended length, then it is just simply acting, there's a gravity which is pulling it towards the center of the earth, okay, which is this. So finally, what do we get? We will get a force which is consisting of two parts, one along the direction from the center of the earth to the object and one perpendicular. The along the direction is 1 plus L squared by 8r squared 2 minus 3 sine squared psi a1 minus L squared 8r squared sine 2 psi into a2 with a minus sign here. And likewise, we can find a torque which is acting on the object, extended object, which is minus gmm L squared by 8r cube. So as usual, as I mentioned, if this L by R tends to 0, so then we can drop this term, okay, then we get the usual that there is only a force which is acting along this direction. So what have we done? So basically I am showing you that if you have an extended object, you can think of a long spaceship which is orbiting the earth, okay, not a small current satellites, but a long spaceship, let's say 1 kilometer long spaceship with of certain mass m, and this is the mass of the earth. So not only will there be an attractive force along the direction, which is this term, there will be a term which is perpendicular to that, and it will also experience a moment. Numerical example, okay, of a long satellite near the earth. So let's say the satellite mass is about 100 tons and it is a distance of 200 kilometers from the surface of the earth, and initial tilt, that psi, is 80 degrees. So if psi were 0, then again there is no perpendicular term, okay, and if there is no moment also. So, and for L equals 1 kilometer, and this is mass is, as I said, we have randomly chosen some numbers, 100 tons, which is not, later on I'm sure there will be satellites and spaceships which are really long, maybe not, maybe in the next 30, 40, 50 years. So then we have this mass of 1 into 10 to the power 5 kg, mass of the earth is known, radius of the earth is known, gravitational constant is known, and if you substitute all that in this formula, what you will get is there is a force which is along the radial direction, which is minus 9.2316 into 10 to the power 5. But there is also a small force, because see, this is 10 minus 4 newtons, which is perpendicular to that. And moreover, there is also a small moment, okay, and I don't know whether it is small or large, but there is a moment which is minus 6.0063 into 10 to the power 3. So if you have a long satellite which is rotating about this earth, you will have a gravitational force, the normal gravitational force pulling it towards the center, but there is also a force which is perpendicular to the satellite and also a torque. So next, we want to look at this concept of something called generalized forces. Okay, so what do we have? We have a rigid body B, our old rigid body B. There is a point OB in which we have another coordinate system xb, yb, zb. The B coordinate system is fixed with the rigid body. The reference coordinate system xa, ya, za is here, and the origin of the B coordinate system is given by AR, and then there is a force F and a moment which is acting on this B coordinate system or on the rigid body at this point. The origin of this B coordinate system or this rigid body has a velocity a v o b and also some angular velocity a omega b. Okay, so this is what we have. We have a rigid body in 3D space with a fixed the coordinate system xb, yb, zb. The origin of this rigid body or a point on this rigid body has a velocity v and angular velocity omega, and there is a force and a moment acting on this rigid body. So now this rigid body can be represented by this position vector and a rotation matrix ABR. We have seen that. And this is with respect to, so B with respect to A. There is an external force Fx, Fy, Fz vector, okay, column vector, and Mx, My, Mz, which is acting on the rigid body. I could represent the rigid body in this way, some position vector, let's say x, y, z, and a rotation matrix which have three independent quantities. I could also represent it by some other coordinates. So let's call these coordinates qi, and for the sake of naming them, we'll call them generalized coordinates. So I can represent a rigid body with some other coordinates qi. So for example, instead of x, y, z, I could have spherical coordinates, or I could have cylindrical coordinates. Instead of rotation matrix, say three Euler angles, I could have Euler parameters, or I could have some other way of representing the orientation of this rigid body. So now we have these external forces given by Fx, Fy, Fz, and moments given by Mx, My, Mz. So this is with respect to the xyz position vector. Can we obtain a representation of these external forces and moments corresponding to this new set of coordinates qi, okay, which I have defined to represent this rigid body? And what are they? So that is the goal. We want to look at external forces and moments corresponding to these generalized coordinates qi. Okay, and how do we find this out? We use this very well-known principle called principle of virtual work. Okay, what does the virtual work principle says? That the work done by F and M for an infinitesimal displacements delta r, so remember this is r, so the small displacement delta r, and also at infinitesimal rotation delta theta. Okay, so what is the work done by this external force and moment? It is F dot delta r plus F m dot delta theta, right? This is the usual formula of work. And this is the expression delta W. So this is a scalar. We are taking two dot products on the right hand side. This is a scalar. So by the principle of virtual work, what we will say is this delta W is same as Qi delta Qi. So Qi's are the generalized forces, delta Qi are the generalized coordinates. So what is the work done by these forces? Generalized forces, it is Qi delta Qi, and again summed over I equals 1 through n. Okay, so this is the work done due to F and M, and this is the work done due to the generalized forces displacing by generalized coordinates delta Qi. So both of these two must be equal. That is the whole idea of principle of virtual work. So we can, let's go a little bit more. So we have this AR. So we can write this AR, and I will show you examples, as a function of Q1 through Qn. So what is this delta R? It is nothing but the partial derivatives of this function with respect to Qi into delta Qi. So this is the standard form of writing what is dq. So instead of writing dr small dr, we could have written this as also dq, and then but the same thing is I'm writing here. Likewise, for theta, I can write some function g of q1 through qn, and delta theta, which is the infinitesimal rotation, can be written also as the partial of g with respect to qi into delta qi. So what is the issue here? the issue here is that there could be many representations of G, okay, of theta. So I can have G in one form, which is Euler angles. I can have Euler parameters. I can have K and phi. I can have quaternion. So there are various different G's which are possible. Okay. However, whatever is the representation of position and orientation, we can also find the angular velocity and the linear velocity of this point. This is well defined. So this could be the space fixed angular velocity, which is r dot r transpose, and this could be the derivative of the position vector. So now, by the principle of virtual work, since the work done by the external forces F and M should be equal to the work done by the generalized forces Qi and del Qi, we can also obtain Qi in this form, which is F dot partial of velocity with respect to Q dot and M dot partial of angular velocity with respect to Q dot. Okay, so remember what is velocity? So this you can think of as d position by dt, and this also Q dot is dq by dt. So this is the partial of position with respect to Qi, which is the same as here. Okay, the angular velocity part is much, instead of doing it this is much easier. Actually, we don't need to find the linear velocity. We can just do this. This is straightforward. Position vector partial with respect to Qi. But for angular velocity, this delta theta is not so easy to understand. And there are many ways of representing infinitesimal rotations. Okay, so we can do this. So now we have an expression for Qi, which is the generalized force or the force corresponding to a generalized coordinate Qi. And in English, what does this mean? This is nothing but a force which is acting along or corresponding to a generalized coordinate Qi. Okay. This is a scalar. That is very important. Capital F and M, they were vectors. Generalized coordinates are always scalars. So we will look at many examples, but the basic idea is that I have some capital or boldface F, which is a force, and a moment which is acting on this rigid body, but I am representing the position and orientation or the configuration of the rigid body instead of x, y, z and rotation matrix, or instead of x, y, z and some angle theta, we are going to use some generalized coordinates which are Qi. So what is the corresponding force which is along that Qi direction, roughly speaking? Okay, so this Qi could be both force and or a moment, depending on what this small Qi is. Okay, so if this small Qi is a displacement like x, y, z, then this capital Qi would be a force. Whereas if this small Qi is a rotation, then capital Qi will be a moment. So let's look at an example, a very simple example. So what do I have? I have a mass m which is acted upon by a force, and this location of this mass is determined by this x. Okay, so what is this force? It is F is 1, 0 along a column vector. It is acting along the x-axis. So there is only one generalized coordinate for this mass. Okay, it is obvious. So Q is nothing but x. It's the same quantity, whether we describe this mass by x or we call some other quantity Q, and Q is nothing but x in this example. So what is R? R is Q into 1, 0. So this is along the x direction. So x and y is 0. What is delta R? Which is partial of R with respect to Q into dq. So this is 1, 0. Okay, the derivative of this is 1, 0 into delta Q. What is the virtual work done by F? F dot delta R, which is F into dq. And this will be equal to Q into dq, right? Okay, So Q is nothing but F in this case, which is expected, which is obvious. So for this simple one-dimensional problem of a mass being pushed by a force F, the generalized force is same as the Cartesian force, or the force along the x direction. So the next example for generalized forces, we'll look at the case of a simple pendulum. Okay, so this picture shows a simple pendulum. So basically we have a bob of mass m. There is a massless rod of length L. There is a torque which is acting here. This angle from the vertical is theta, and it locates this bob. I could also locate the bob with some x and y coordinate. Just to make the problem a little bit more interesting, we assume that the end of the bob and this mass m, a force with components fx and fy with respect to the zero coordinate system is acting, and the angle of the force is also theta. So as I said, there is a mass m at the end of a massless rod of length L. The external force acting at Fm is Fx and Fy with components Fx and Fy. There is also an external moment acting at O. This is the torque, and it is acting along the z-axis, which is x cross y. So as I said, there are two possible choices of generalized coordinates. So I can describe this simple pendulum with either x comma y, which is the mass and the bob coordinates, or I can also use theta, which is the angle from the vertical. So let us try and find the generalized force Q for the generalized coordinates Q equals theta. So for this pendulum, the position vector of this mass m is given by L sine theta and minus L cos theta. Okay, so remember the y-axis is above, so hence the y-coordinate is minus L cos theta. The derivative of this position vector is L cos theta and L sine theta. So del r as a vector is this L cos theta, L sine theta column vector into delta theta. So the generalized force for Q, which is same as theta here, is capital Q, which is the generalized force, is given by Q into delta theta is this vector Fx, Fy dot product with delta r. So that is given by L cos theta, L sine theta into delta theta. And we also have a component of the generalized force due to this torque, which is tau into delta theta. So hence you can simplify and you can cancel delta theta from both sides, and you will get Q theta is Fx into L cos theta plus Fy into L sine theta, which is coming from this part, plus tau. So what you can see here is that the generalized force is a scalar, Q theta. More importantly, because the variable is Q, which is same as an angle, the generalized force has units of torque, which is Newton meters. Now let us look at generalized forces and multi-body systems. So what we have here is a serial chain with, let's say, 3 bodies shown here. Actually, n, the last body is n. So this is body I minus 1, body I plus 1. So these are n rigid bodies connected by joints. And then there are external forces and moments which are acting on these rigid bodies. So the force here is Fi minus 1, and I'm going to call the moments as Ni minus 1. Okay, so on the ith body we have a force Fi which is acting and a moment Ni, and so on. So the serial chain can be described by n generalized coordinates. So let's say there are n generalized coordinates which describe the serial chain. Most of the time we have these joint variables. So for example, if this joint I is a rotary joint, then we'll have theta as the joint variable. If this joint is a sliding joint, then we have P as a prismatic joint. If you have some other joints, for example, a spherical joint, then you'll have 3 such coordinates. So this system of connected rigid bodies in the form of a serial chain can be described by Q1 through Qn, n generalized coordinates. So the generalized force corresponding to a generalized coordinate Qi can be determined by this formulation, which is that you take the dot product of F with respect to partial dVi by dQi dot. So remember, dVj by dQi dot is dVj is d position by d theta, okay, or some q, and Qi dot is dq divided by dt. Okay, so we have basically d position by dq here, and we are trying to take the dot product of F with that. So this is like delta R. Similarly, this term is m dot partial of angular velocity with Qi dot. So this is like in some sense similar to delta theta. But this is easier because in delta theta, remember we had discussed that the orientation can be described by various kinds of representations, whereas the angular velocity is a vector. So this partial derivative of angular velocity with respect to Qi dot will be a vector, and I can find the dot product with the moment. So this is like the work done. F into delta R is also like the work done, and then we can equate that to the result of the generalized force into some delta Q, and then we can arrive at this expression Qi is given by this. So in the robotics community, this right hand side, which is F dot partial of velocity with respect to Q dot plus m dot partial of angular velocity with respect to Q dot, can be reorganized in this form. Okay, so this is very well known in robotics community as the Jacobian matrix. So the right hand side is nothing but Jacobian transpose a quantity, which is this F, which I have written, and this F is nothing but capital F comma m. Okay, so it's a vector containing both F and m, so 6-dimensional actually, and the left hand side is V comma omega. So this Jacobian matrix relates the V, the linear velocity, and the angular velocity to Q dot. Okay, so let's not, this is a well-known way of representing the generalized forces in the robotics community. Here we are going to use this formula, which is that the generalized force Qi corresponding to a generalized coordinates Qi, small qi, can be written as a dot product of forces times the partial of velocity with Qi dot, and similarly moments dot product of the angular velocity with Qi dot, and of course summed over j equals 1 through n. In parallel chains, we don't have any unique choice of generalized coordinates. Okay, and I will show you some examples with a 4-bar mechanism, which is a very simple parallel chain, that depending on how you write the loop closure equations, we can have a variety of ways of choosing generalized coordinates. Secondly, we don't have a clear and obvious output rigid body. Okay, so we have these two problems, that we have loop closure equations which can be written in different ways, and we do not have a final end from which we can say that, okay, this is the force which is acting in the output. Because of that, we have some more complications. We cannot really find out what are the generalized forces Qi for a given generalized coordinate Q small qi. Okay, it will depend on what is the output body and also what are the loop closure constraint equations. And I will show you some examples with a 4 bar. But let's continue. Let's take a very simple 2 degree of freedom or two rigid bodies connected by two rotary joints. This is probably the simplest possible multi-body system. So we have what is called as a double pendulum. So we have one pendulum with a mass at one end, then another link and mass at another end. Okay, and we will assume that there is a torque which is acting at the first link, there is another torque which is acting at the second link, and then we have these forces Fx and Fy acting at the tip. And the mass, this is M1 and this is M2. These links are massless rods, just like the simple pendulum. So this is called as a double pendulum. The generalized coordinates in this case, Q's are θ1 and θ2. Okay, we have θ1 again from the vertical and θ2 is a relative angle. We also have an external force acting at this mass M2, which is Fx and Fy, column vector with Fx and Fy. There are also external moments acting at the first and second joint. These are τ1 and τ2, and it is coming out of the page. It is along the vector x cross y. So the position vector of this mass M1 is denoted by R1. It is L1 sine θ1 minus L1 cos θ1. So you can see that the y coordinate is minus L1 cos θ1 and the x coordinate is L1 sine θ1, this perpendicular distance. Likewise, the position vector of the mass M2 is this L1 cos θ1 plus L2 cos θ1 plus θ2. That will be the y coordinate. Again, both are with minus sign. And likewise, the x coordinate will be L1 sine θ1, which is this distance, plus L2 into sine θ1 plus θ2, which is this quantity here. So we have the position vector of both these masses, R1 and R2. We can find the delta R1, which is the derivative of this, which is L1 cos θ1 and L1 sine θ1 into delta θ1. Likewise, delta R2 is L1 cos θ1 plus L2 cos θ1 plus θ2 into delta θ1, and then L2 cos θ1 plus θ2 into delta θ2. So basically we have to take the derivatives and we use chain rule. Okay, so we will get one term here involving cosines, and similarly the y component derivative of cos θ1 will become sine θ1, and this minus sign will go away, and so we have L1 sine θ1 plus L2 sine θ1 plus θ2 into delta θ1, and then L2 sine θ1 bracket θ1 plus θ2 into delta θ2. So we have position vectors and we have the partials, we have the derivatives of the position vector. So the generalized coordinate will be nothing but f dot partial of this velocity. So dv by dq dot is similar to dr, delta r1, and for I j equals 1, for j equals 2, it will be this vector here. Likewise, the mj dot this will be from j equals 1 to 2 will be again omega. So what is the omega? That is the angular velocity of this link, that is θ1 dot, and the angular velocity of this link is θ1 dot plus θ2 dot. It is not shown here, but you can see. And both of these angular velocities of these links are coming out of the page. They are along the z-axis. So remember, τ1 is along the z-axis and the angular velocities are along the z-axis, and the derivatives of that will be just the z-axis. Okay. So hence, the generalized force for θ1 can be obtained as τ1 plus fx into L1 cos θ1 plus L2 into cos θ1 plus θ2 plus fy into L1 sin θ1 plus L2 into sin θ1 plus θ2. We just expand this. And the generalized force corresponding to Q of Q2, which is in this case θ2, remember Q is θ1 and θ2, will be nothing but the torque tau 2 plus the moment of this fx and fy in some sense. Here also we have these moments of this fx and fy as seen by this first link. So in this case it is fx into L2 cos theta 1 plus theta 2 plus fy into L2 sin theta 1 plus theta 2. Let's take one more example, and this is an example of a pendulum on a cart. So what we have here is a mass which can slide along the x-axis, but on this mass we have a pendulum, a simple pendulum. So the mass of this block is capital M, and then there is a mass of M, there is a moment which is acting on this link. The mass of this block is small m1, and then we have this mass of this bob which is m2. And again, let's to generalize or in some sense make it a little bit more challenging, we have a force fx and fy which is acting on this mass, and there is a force which is acting on this mass which is along the x direction. So the generalized coordinates in this problem are x and theta. So we have this location of this sliding mass by x, and then we have this location of this bob by theta. So the purpose of this example is to show that we can have generalized coordinates, one which is a linear measure which is like x, and theta which is an angular variable. So the external force acting at m1 and m2 are f, 0 and fx and fy. The external force acting at the first joint is this moment m. The position vector of this mass m1 is x, 0. You can see that it is clearly, so this is 0, 0, this is x, 0. The position vector of mass m2, which is this r2, which is x plus some L sine theta. This perpendicular distance is L sine theta, and the y coordinate is minus L cos theta. So we can have this vector r1 and r2. The derivative of these position vectors, or delta r1, is 1, 0 delta x, and similarly delta r2 is 1, 0 delta x plus the derivative of this term which is L cos theta, sin theta derivative is L cos theta, minus L cos theta which is L sin theta into delta theta. Okay. So the generalized force, again using the same formula for corresponding to x, which is qx, will be given by f plus fx. So there is a component fx for this which is along this direction. The generalized force for x is f plus fx, whereas the generalized force for theta will be fx into L cos theta plus fy into L sin theta. So basically this is the moment of this force fx and fy as seen at this point. Okay, so qx has units of Newton and q theta has units of torque, Newton meter, and that sort of comes from what was the choice of q. In one of them, this is x, which is a linear measure, and theta, which is an angular measure. So the generalized force corresponding to the linear measure will be in newtons, and the generalized force corresponding to the angular measure will be torque. So let's take another example of generalized forces in a multi-body system. And we will take the example of a very well-known simple multi-body system, a parallel mechanism or a 4-bar mechanism. Okay, so the 4-bar mechanism is shown in this figure. It consists of a link 1, which is called the crank, link 2, which is also sometimes called as the coupler, link 3, which is in this case chosen as the output link. Sometimes the coupler is the chosen output link, but in this example we will assume that the link 3, which is the output link, as chosen. Additionally, there is a variable theta 1 which denotes the or shows the rotation of this crank. The length of this crank is L1, the length of this coupler is L2, and the length of the output link is L3, and the rotation of this output link with respect to the horizontal is phi, and the distance between these two fixed points or the base is L0. Okay, so this has one loop, so you can start from here, O, go here, come here, and then again come back here. So this is a 4-bar mechanism with one loop, and this is a parallel mechanism. So we want to study the generalized forces in this multi-body system. So what we have here is a moment which is acting on the crank. Then we will assume that there are these two forces, F2 and F3, which are acting at the end of the crank and the end of the coupler, or the end of the output. So the generalized coordinates which we choose for this 4-bar mechanism, considering this is the input and this is the output, is theta and phi. The external moment acting at the first joint is denoted by M1. This is along X cross Y, which is basically coming out of the page. And the external force acting at the end of the crank and coupler are F2 and F3 respectively. Okay, so these are planar vectors. The position vector of the crank end, which is this here, is R1, denoted by R1. It is L1 along cos theta and L1 along sine theta. The y coordinate is L1 sine theta. The position vector of this end, which is the coupler end or the output end, is given by R2, and that is nothing but this vector plus this vector. So this vector is L0 along the x direction, and then L3 cosine phi, which will give me this some distance, and then L3 sine phi, which is the vertical distance. So I know the position vector of these 2 points. The delta R1 and delta R2 can be obtained by the derivatives of these vectors, which is minus L1 sine theta delta theta and L1 cos theta delta theta. This is delta R1. Delta R2 is the derivative of this vector, R2 vector, which is given by minus L3 sine phi into delta phi plus L3 cos phi delta phi. So you can see that the derivative of L0 will go away because it's a constant, and then we are left with this minus L3 sine phi delta phi and L3 cos phi delta phi. So the generalized force is nothing but the F dot, the derivative of the position with respect to theta and phi, or the derivative of the velocity with respect to q dot. Okay, so whichever way you use, you can see that the q theta will be m1, which is the derivative of the moment, or derivative of the moment dot derivative of the angular velocity with respect to q dot. So this will be m1 because the angular velocity will be theta dot, and so this is m1 minus fx2 L1 sine theta and plus fy2 L1 sine theta. So basically it is the moment of this force F2. We are assuming that the force F2 has components fx2 and fy2, and this is the moment of this force as seen from here. Okay, so hence we will have a term which is pure moment, which is this acting at this crank, and then the force into some lengths. Okay, this is the arm, F into some R cross F type of term. Generalized force Q phi will be nothing but F3. Okay, so the components of F3 are Fx3 and Fy3. So this is minus Fx3 L3 sine phi and Fy3 L3 cos phi. So in this example, we have not assumed any other moments, only one moment. So the moment dot d omega by dq dot will only show up here in q theta, not in q phi. And in this case, both these generalized forces are Newton meter, because we are starting with generalized coordinates which are angular measures, theta and phi. So the generalized forces will be in torques, in Newton meter. The generalized force can be different, and I will show you an example again with this 4 bar, that I could now, instead of choosing theta and phi as my generalized coordinates, I could have also chosen some angle theta, one more angle here and one more angle here. This is what we had discussed in earlier. If I break this chain at this point, so in this example I am breaking the chain at these 2 points. Remember, there is a formula for the degree of freedom of this 4 bar mechanism. The degree of freedom of this is 1. So whatever way you choose the generalized coordinates, there must be a relationship between phi and theta, which we have derived earlier, or if you choose the generalized coordinates as theta 1, phi 2 and phi 3, then there will be two relationships between these two generalized coordinates with respect to theta 1. Okay, loop closure constraint equations. We have discussed this earlier. So let us continue with this 4 bar mechanism again. And now we are saying that we will break it up at this point here, OR, which is the other fixed end. And we will look at, make the problem a little bit more interesting. We'll assume that there is a moment which is acting at the input link 1. There is also another moment which is acting on this link 2, which is M2. And there is a moment which is acting at M3. And like before, we have a force F2 and an F3, which are acting at the end of the crank and the end of the output link or end of the coupler. So the position vector of this point P1 is given by L1 C1 plus L1 comma L1 S1 0. So we are intentionally writing it as a 3D vector, although everything is happening in the plane. And the reason why we are writing in 3D is the angular velocity vector is actually along the z-axis. The position vector of this point P2 is nothing but L1 into cos theta 1 plus L2 into cos theta 1 plus theta 2. Likewise, it is L1 into sine theta 1 plus L2 into sine theta 1 plus theta 2, and again z coordinate is 0. The P3 point is given by L1 C1 plus L2 C12 plus L3 C13. I am choosing this theta 1 angle, and this is phi 2 angle, and this is phi 3 angle. So C12 here corresponds to cos of theta 1 plus phi 2. C1 corresponds to cos of theta 1. So C123 is cos of theta 1 plus phi 2 plus phi 3, and so on. So P3 is given by L1 C1 plus L2 C12 plus L3 C123, and L1 S1 plus L2 S12 plus L3 S123, and again z coordinate is 0. The angular velocity of the first link is theta 1 dot along the z-axis. The angular velocity of the second link is theta 1 dot plus phi 2 dot. And angular velocity of the third link is 0, 0, theta 1 dot, phi 2 dot, and phi 3 dot. Okay, so you can see, since these angles are relative angles, okay, so theta 1 is this way, phi 2 is from the extension of this link to L2. So we are using anti-clockwise positive. So this is the phi 2 is the relative angles, hence the angular velocity will be theta 1 dot plus phi 2 dot for this link. And same thing for this link. It will be theta 1 dot plus phi 2 dot plus phi 3 dot. So the q theta 1 is nothing but m1, which is along the z-axis, into partial of omega 1 with theta 1 dot, m2 into dot product of partial of omega 2 with theta 1 dot, m3 partial of omega 3 with theta 1 dot, plus f2 into partial of position vector with theta 1 and F3 dot partial of position vector P2 with theta 1. Okay, we could have also taken the velocity of point 1 with theta 1 dot and velocity of point 2 with theta 2 dot or theta 1 dot. What is F2? We are assuming F2 has components Fx2 and Fy2. F3 has components Fx3 and Fy3. The Z components are 0. So if you simplify all these things, we will get M1 plus M2 plus M3 because the partial of omega 1 with theta 1 dot is along the Z axis. The partial of omega 2 with theta 1 dot is also along the Z axis. Omega 2 is actually theta 1 dot plus phi 2 dot. Okay, so omega 2, when you take the partial, you will again get 1001. Okay, and same thing with omega 3 with theta 1 dot. So omega 3 is also a function of theta 1 dot. Of course, it is also a function of phi 2 dot and phi 3 dot, which will show up when we find the Q corresponding to phi 2 and Q corresponding to phi 3. Likewise, the dot product of the force with respect to the partial of P1 with theta 1 we can compute because we know the position vector. We can find out what is this. Okay, P1, remember, was L1C1 plus L2C12 plus, that is the x component. Y component was L1S1 plus L2S12. So we can find the partial of that position vector with respect to theta 1. Likewise, we can find the partial of the position vector of 2 with respect to theta 1. So all these quantities are known, and if you now substitute, we'll get M1 plus M2 plus M3, and then you'll have F dot minus L1S1, L1C1, and Fx3, Fy3 dot minus L1S1 minus L2S12, L1C1 plus L2C12. Remember, S12 is nothing but sine of theta 1 plus phi 2. So Q of theta 1 is given by this expression, M1 plus M2 plus M3 minus L1S1 Fx2 plus L1C1 Fy2 minus L1S1 plus L2S12 whole into Fx3 and L1C1 plus L2C12 into Fy3. So basically we have some moment components coming from M1, M2, M3, and then the moment of these forces F2 and F3. Q of phi 2 will now contain only M2. M1 will not be there because omega 1 is not a function of phi 2. Omega 1 is only theta 1 dot. So M2 dot omega 2 divide partial with phi 2 dot and M3 of omega 3 partial of phi 2 dot and F3 dot P2 with respect to phi 2, and so hence we will get all these terms. Okay, so we will get terms which are M2 plus M3 minus Fx3 L2 S12 plus Fy3 L2 C12. Similarly, Q of phi 3 will now contain only M3. There is no other force which is acting which will affect this generalized force. So for a generalized coordinates Q, which is now theta 1, phi 2, phi 3, there are three generalized forces Q theta 1, Q phi 2, Q phi 3. All three generalized forces are non-zero. Okay, we saw terms. The degree of freedom of this four-bar mechanism is 1. So what it means is phi 2 and phi 3 are related to theta 1 through loop closure equations. We had discussed these loop closure equations earlier. So only Q phi 2 and Q phi 3 are not supported by R joints, okay, which are present at P1 and P2. So one might think that since Q phi 2 and Q phi 3 are non-zero, they are coming from the R joint. Okay, but that is not strictly correct. There is no actuator for phi 2 and phi 3. So the equation of motion with these loop closure constraint equations will ensure consistency. that we have only one actuator which is corresponding to theta 1. There are no actuators corresponding to phi 2 and phi 3 because we cannot have more than one actuator in a 4-bar mechanism. It has only degree of freedom 1. Okay, so the sort of apparent inconsistency that q phi 2 and q phi 3 are non-zero will be sorted out when we derive the equation of motion and we take into account the loop closure constraint equations. So in summary, I have discussed external forces and moments. So we looked at what are contact forces, we looked at what is gravity, we looked at what is spring, k into x, and we looked at what is damping, which is like cx dot plus c1, some constant and some term which is proportional to the velocity. Then we looked at generalized coordinates and forces, and we obtained these generalized coordinates and forces. We choose the generalized coordinates, and the generalized forces are obtained using the principle of virtual work. So the work done by Fx, Fy, Fz and Mx, My, Mz is equal to Q into some delta theta. So on a single rigid body, this corresponds to 3 translation and 3 rotations. On a multi-body system, we could have different coordinates. The generalized coordinates could mean different. Okay, if you have a serial chain, they are the joint variables. If you have a parallel chain, it depends on how you break the parallel chain and how you model the kinematics of the parallel chain, and then we get a different set of generalized coordinates. Okay, so there are many choices of generalized coordinates in parallel chains, and for the 4-bar mechanism I showed you 2 possible ways. So once I had an input angle and an output angle, crank and the output. In other case I had 3 angles. So the different generalized coordinates which you choose for a parallel chain will give to different generalized forces. Okay, and they are different. So we need to keep in mind what we are exactly doing to figure out what the generalized forces and what the generalized coordinates are.